Right now, while you're watching this, roughly 5 billion people are connected to the same network. Every phone call, every text, every single packet of data moving across the internet passes through a routing system that nobody elected, nobody officially controls, and almost nobody understands. The entire architecture was sketched on 2 napkins at a table in Austin, Texas in 1989, and the phone network underneath it runs on a protocol from the 1970s that has no encryption, no authentication, and no way to verify that the person on the other end is who they claim to be. In October 2021, a single misconfigured command erased Facebook, Instagram, and WhatsApp from the internet for 6 hours. Not hacked, not attacked, just gone. Because one routing update told the rest of the world that Facebook no longer existed. But that outage was a warning, not the worst-case scenario. The worst case is something most engineers don't like to talk about publicly. This is how the system that routes every call and every packet on Earth actually works, and why it's more fragile than almost anyone realizes. Every time you make a phone call or send an SMS, your carrier doesn't handle it alone. Your device connects to a local tower, but that tower has to figure out where the other person is, which network they're on, and how to route the connection across potentially dozens of intermediate carriers. The protocol that orchestrates all of this is called Signaling System 7, or S7. S7 was designed in the mid-1970s and standardized through the 1980s. It was built for a world where every telecom operator was either a government monopoly or a tightly regulated utility. The assumption baked into the protocol's DNA was simple. If you're on this network, you're trusted. No passwords, no verification, no encryption, just raw, open signaling between carriers. That trust model made sense in 1980. Fewer than 20 organizations on the planet had access to 7 infrastructure. Today, hundreds of carriers, resellers, SMS aggregators, and third-party routing services connect to it. And because the protocol never evolved to include basic authentication, anyone with access can send commands that reroute calls, intercept text messages, or track a phone's location down to the nearest cell tower. In 2017, attackers exploited 7 to bypass two-factor authentication on German bank accounts. They intercepted SMS verification codes in real time, redirected them to phones they controlled, and drained customer accounts before anyone noticed. The banks had done nothing wrong. The customers had done nothing wrong. The protocol itself was the vulnerability. The Electronic Frontier Foundation formally petitioned the FCC in 2024 to investigate 7 security, noting that even carriers who have shut down their own 2G and 3G networks remain connected to 7 to support international roaming. The protocol's replacement, called Diameter, was supposed to fix these problems for 4G and 5G networks. But security researchers have found it suffers from many of the same fundamental design flaws. So the system that routes your phone calls was designed before the internet existed, assumes every participant is trustworthy, and has known exploitable vulnerabilities that have been documented for over a decade. But it keeps running because replacing it would require coordinated action from every telecom operator on Earth simultaneously. The internet's routing system has a different origin story, but the trust problem is almost identical. In January 1989, at the 12th meeting of the Internet Engineering Task Force in Austin, Texas, 3 engineers sat down at a table. Yakov Rector from IBM, Kirk Lauheed, and Len Bosak from Cisco. They needed a protocol that could replace the aging system the early internet used to move data between networks. What they sketched on 2 napkins that afternoon became the Border Gateway Protocol, or BGP. It has been the routing backbone of the global internet ever since. Here's how it works. The internet isn't one network. It's roughly 83,000 separate networks, each called an autonomous system. Your home, ISP, is one. Google is one. Amazon Web Services is one. Every university, every government agency, every major corporation that connects to the internet operates as its own autonomous system. BGP is the protocol these systems use to tell each other what traffic they can carry and where they can send it. Think of it as a global address book that updates itself continuously. When a new network comes online, it announces its presence through BGP. When a network goes down, BGP routes traffic around it. On an ordinary day in May 2025, BGP routers processed over 700,000 route updates in a single 24-hour period across more than 1 million tracked address prefixes. The system is handling a staggering volume of decisions every second. But here's the critical flaw. BGP operates almost entirely on trust. When a network announces that it can route traffic to a specific set of addresses, every other network believes it. There is no built-in mechanism to verify that the claim is true. In February 2008, the Pakistani government ordered its national telecom to block YouTube within the country. The engineers at Pakistan Telecom created a BGP announcement that essentially told the internet they were the correct destination for all YouTube traffic. That announcement leaked beyond Pakistan's borders. Within minutes, YouTube was unreachable for users across most of the world. A domestic censorship order accidentally became a global outage because BGP had no way to distinguish a legitimate routing claim from a false one. The Facebook outage of October 2021 worked differently, but exposed the same underlying fragility. Facebook's own engineers pushed a configuration change that accidentally withdrew all of the company's BGP route announcements. In BGP terms, Facebook told the entire internet that it no longer existed. Every router on Earth updated its tables and stopped sending traffic to Facebook's servers. The company's internal tools ran on the same infrastructure, so engineers couldn't even log in remotely to fix the problem. They had to physically travel to data centers and reconfigure routers by hand. 6 hours. Roughly 3.5 billion users affected. Not because of a sophisticated attack, but because of a routine maintenance command that interacted with the trust-based system in an unexpected way. And these aren't edge cases. In 2017, a Russian state telecom briefly rerouted traffic belonging to Visa, MasterCard, and several major financial institutions through its own network. In April 2021, an Indian carrier accidentally announced over 30,000 BGP routes it had no authority to claim, causing a 13-time spike in misdirected traffic that impacted Google, Microsoft, Akamai, and Cloudflare across more than 100 countries. In 2022, attackers used a deliberate BGP hijack to steal approximately $1.9 million in cryptocurrency from a South Korean exchange. The obvious question is why these systems haven't been replaced. The answer is the same for both S7 and BGP. They work. Not perfectly, not securely, but reliably enough that the cost of replacing them has never outweighed the cost of living with their flaws. For 7, replacement means convincing every telecom carrier on Earth to migrate simultaneously to a new signaling standard. Any carrier that stays on 7 becomes a bridge back to the old vulnerabilities. For BGP, there's a cryptographic upgrade called RPKI, Resource Public Key Infrastructure, that allows networks to verify route announcements. But adoption is voluntary. And as of early 2026, coverage remains incomplete. A system that only works when everyone participates doesn't work until everyone participates. The deeper issue is structural. Both protocols are coordination problems, masquerading as technical problems. The technology to fix them exists. What doesn't exist is a governance mechanism that can compel 83,000 autonomous systems and hundreds of telecom operators across every jurisdiction on Earth to upgrade in lockstep. So every phone call you make still travels through a protocol designed before the fall of the Berlin Wall. Every packet of data still routes through a system sketched on napkins at a conference table in 1989. And the whole architecture holds together not because it's been engineered for security, but because the overwhelming majority of participants on any given day happen to be telling the truth. The system works until the day it doesn't. And when that day comes, there is no backup, there is no manual override. There is just 83,000 networks, all trusting each other, hoping that none of them made a mistake. If you want to see what happens when one of these invisible systems actually fails at scale, that video is on screen now. Subscribe for more investigations into the infrastructure you rely on every day but never see.